This video is a demo of a recording thermometer like the one that you'll be making in Lab 2. It corresponds to section 8.8 of the Applied Analog Electronics textbook. Now, the recording thermometer itself is very simple. It consists of a thermistor, here in a water bath, since that's what I'm recording the temperature of, a resistor, which I'm not really showing the size of because part of your design is to figure out what size resistor you want to use, wires connecting the thermistor to the breadboard, another pair of wires here, the black wire and the red wire, that provide power to the voltage divider. And I'm not showing you which way around the voltage divider is going, whether the thermistor is closer to the 3.3 volts or closer to the ground. You have to decide that also. 3.3 volts is coming along the red wire along the outside there from the TCLC, and the ground is coming via the black wire from the black wire here from the TCLC. So we have both the 3.3 volts and the ground coming from the TCLC. The middle of the voltage divider, which is the output of the voltage divider, is going over to pin A0 on the TCLC. So if I run Teradak, I should be able to record the voltage at that pin, the output of the voltage divider, and get voltage as a function of time. Okay, one thing I've done that's a little bit differently than what is suggested in the book is that I have soldered the wires onto the thermistor here rather than using clip leads. I was having trouble with the clip leads either not making contact or cutting the wires, and so rather than fuss with the clip leads, I soldered on ordinary hookup wire and wrapped them with electrical tape so they wouldn't short together. And that way I can put this into the water just using a clip here to hold it so I don't have to handle it. You do need the thermometer a little bit for this part of the lab, and that you need to verify that the formulas you've come up with for what should be the voltage at different temperatures based on the calibration of the thermistor that you did, you need to verify that those actually work, that you got your formulas right and the voltage come out being what you expect at a few different temperatures. So one high temperature, one low temperature, one middle temperature. If you've got that so that, okay, I checked it at 80 degrees C, I checked it at 25 degrees C, I checked it at 5 degrees C, and the voltages there are correct, then you can be pretty confident that you've calibrated your thermistor correctly, you've got your formulas correct. If it doesn't come out right, then you've got to figure out, well, is my calibration wrong? Are my formulas wrong? And debug the problem. Okay, so assuming you've got all that done, we can go over to Teradak. Here I'm in the directory one up from the DAQ directory that has the executable, so I'm in the Teradak directory itself. So I can just say Python DAQ here, and it should bring up Teradak, and it sees that there's a board out there that it can use, so I tell it just to go. I don't know why it's ignoring data packet, but we'll add a channel here. I'm adding, the default channel is A0, 10 times a second's fast enough. So I can just hit record here, and the last value here is the current voltage. The DC is the average of them all, the RMS is the standard deviation of them all, and if this thing is hot water cooling down, I should be able to see that voltage dropping. Let's see if I can make this a little bigger here, so we might be able to see some motion here. It started, the average here has been 1.55 and it's down to 1.547. It is dropping, and that's what I would hope to see if the water there is cooling. Now it's not cooling very fast, so the voltage isn't dropping very fast. You can see it's just moved a tiny little ways here. And so you want to record this once you've confirmed that it is moving in the right direction, so you've got the circuit working correctly. Just record it for a long time. It doesn't cost you anything to let the thing run. And up here we can see this number here that's how many measurements it's made so far. So it's made 700 measurements. That's easy. you're not having to make the measurements, it's doing it for you. You probably should put some notes in here about what size resistor you used, what your experimental setup is, what temperature did the water start at. For instance, you can measure that with a thermometer, and you can then have a sanity check to say, okay, when I do the plot, and I claimed it started at 60 degrees C or whatever, when I plot it, does it start at 60 degrees C or does it start at 23 degrees C? In which case I know there's something seriously wrong with my computations to go from the voltage, which is all that Teradek records, back to the temperature, which you can do by writing formulas in Gnuplot. Let's leave this thing running and take a look at what we would do with Gnuplot. Now, I did a recording earlier when the water was a little bit warmer, and what I did in Gnuplot is I plotted not the voltage here. Nobody cares what your voltage is. They want to know what the temperature is. So you have to convert the voltage that you measured with Teradek back into temperature in Celsius. And here I did start at about 63 degrees C, and so the fact that this is starting at 63 looks, hey, that's about right. I got those formulas right. In fact, when I was typing this thing up quickly just to do this video, I got one of my formulas upside down and I was going, wait a minute, it's not supposed to go up. The water was cooling down. I've made a mistake. So I looked through where I typed everything. Oh, I did this over this instead of the other way around. Fixed the problem, and now it makes sense. The numbers are correct. There's some constants you will need. One constant is, what's the voltage? That 3.3 volts? It's not exactly 3.3 volts. If we go back and look at Teradek, it's reported here, 3.3054 here, so a little bit higher than 3.3, and that's going to vary from board to board, and it's going to vary somewhat with the temperature of the board also. So you want to record that. Luckily for you, Teradek records that automatically. When you save your file, save the data file, it'll save some metadata at the beginning that just are comments as far as Gnuplot's concerned when it's looking at the data. But you can look at that and say, oh, the 3.3 volts was really 3.3054, and type that in as a part of your Gnuplot script. Okay, so that's really pretty much all you have to do here is get this plot where you have time on this axis, and that's just column 1 of your Gnuplot data file, and then the temperature here, which is going to be some function of column 2. Column 2 is the voltage, so you need to write a function that says what is the temperature in degrees Celsius for a particular output voltage. And you'll have some parameters that you need in order to do that. You'll need to know what is the voltage that you're putting into the voltage divider, what is the characteristics of that thermistor you were using. So there was an R infinity and a B value that you got from fitting the data from your measurements. And then you'll need to know what size resistor did you use for your other resistor of the voltage divider. You should be able to come up with a formula that gets the temperature in Celsius, not Kelvin, from those parameters and the voltage that's recorded in Teradek. And write it as a function so that in the plot command, all it says is something like plot, and then in quotes, the data file, using 1 colon, and then in parentheses, temperature from voltage, whatever you call that function, of $2, so that you've got something that is an easy to read formula, and previously you've defined the functions you need to use. Okay, this is your goal, and you notice that I ran this thing for 800, 900 seconds so that I could see the stuff cooling down. If you really want to, and notice that only got from 63 degrees down to about 51 degrees. If you want it to cool a long way, it takes a long time. Water cools fairly slowly. So you can have plenty of time to do your experiment, and you can just leave the recording running for quite a while if you want to see the exponential decay towards room temperature. Okay, have fun making this recording, and Your goal is to come up with a plot that looks somewhat like this one. You'll be starting from a different temperature, you'll be recording for a different amount of time, but it should show water cooling down. You could also, if you prefer, do very cold water warming up to room temperature, but that's even slower.